Welcome to Ingenium Technology's first webcast. Our presenter today is Dick Walsh, who is an owner and lead analytical engineer at Ingenium Technologies. His wise words, which you are about to hear, come from his 30-plus years of technical leadership, as well as his bachelor's and master's degrees in mechanical engineering from the University of Illinois. Dick is also the holder of 7 patents applicable to aircraft power transmission and actuation systems. Dick's presentation is entitled Failure and Stress Analysis, Lessons Learned.
Parts break because there's too much stress for the material to carry. Too much F, not enough A. Such a simple observation will not reveal just what went wrong. Keep it in mind, however, to help direct your search. If this is a new product which failed early in usage, then a revisit to the actual loads on the part is in order. What was anticipated for loads and what actually happened can be very different. During testing, you likely used the proper loads. Now it is in other people's hands. On the not enough A end, the actual part geometry and material need to be checked. For a new product, what is on the print and what is on the part may well differ. Sometimes a mature product is out there for years and then it turns on you. It comes back in a box with a nasty note attached. Look for fatigue problems. This is often a not enough A kind of problem. If the initial test was short, it may not have revealed fatigue problems. These take time to show up. Sometimes a unit will be returned in many pieces, in a basket. This is something like the aftermath of a street brawl. A lot of damage, and it's not clear who started it. The problem here is to work back to the initial point of failure. What failed first? The person who did the original analysis is often sought out for an explanation of just how could this have happened. I've been on the wrong side of these conversations. Sometimes the suggestion is made to go to a more accurate method of calculation. Rather than a hand analysis, use finite element. Use a finer mesh for the finite element analysis. Do something. Sometimes this is the answer to getting a better picture of what happened. Using font size and color to reflect importance, the more common reason is that the condition or location was never analyzed. For an analyst, this is an even more awkward conversation. As a case on point, this little actuator is loaded from one end to the other in tension and compression. Torque is carried back to the motor. Without going into embarrassing details, there's a small pin which is in the load path. It was overlooked in the analysis. It failed. A careful look at the load path made it clear that the pin was undersized. To avoid this kind of thing, use a detailed load path. For an analyst, this is an even more awkward conversation. As a case on point, this little actuator is loaded from one end to the other in tension and compression. Torque is carried back to the motor. Without going into embarrassing details, there's a small pin which is in the load path. It was overlooked in the analysis. It failed. A careful look at the load path made it clear that the pin was undersized. To avoid this kind of thing, a detailed load path needs to be worked out during analysis. Not everything will need to be analyzed, but a conscious decision needs to be made for each part. In this case, the blue part moves to the right, impacting the stationary red part. This is a dog stop on a large actuator. In the analysis, the horizontal shear area was sized to carry the load. When the actual test was run, one of the parts sheared out at a 45-degree angle at an embarrassingly small load. The combined compression and shear stresses on the 45-degree plane was not anticipated as a failure mode. It does happen that a more accurate method is needed. The pocket in this part carries pressure which has caused the top to dome up. It looks like a standard case for a flat plate fixed on the outside pressure loading. The stress concentration was looked up. Rourke and Peterson at their best. The part failed. Later finite element analysis showed the true picture where the radial growth of the cylindrical section added tension load to the top. A fatigue failure resulted. Let's go back to the basics and look at the drivers and a failure. What are the loads? What is the geometry? And how much stress can be tolerated? The importance of a careful look at the load path was noted in the actuator failure. Examples of a load fight, dynamic loads, and unexpected usage loads will be shown. This is one of the actuators and the cross-ship shafts of an aircraft wing sweep system. One of the concerns is that there be no possibility of one wing being out of position with relation to the other. The cross-ship drive shafts have the ability to drive the full load from either side. There were several ways that the position match was enforced. They disagreed, even for small, acceptable position differences. The full torque of the drive system on each side was applied to bring the two sides together. Failure of the cross-ship drive shaft occurred. This is a load fight. Dynamic loading can occur when there's a resonance condition. This is a blower some 4 feet in diameter. The blades receive minor load variations as they pass static parts. In this case, the impulses happened at the resonant frequency of the blade. Like pushing a child on a swing, each push builds a response. Making things worse, the fatigue allowable is often 1/3 or less than the material ultimate strength. A static load can cause minor yielding at the stress concentration and cause no damage. In a fatigue situation, however, the stress concentration is in play as well as the lower allowable. Shown here is a classic fatigue failure. The arcs of different texture show the path of the fatigue crack. The crack started from the center of the arc. It may have been caused by an initial flaw or just high stresses. There will often be lines in the crack face where the crack edge moved each load cycle. With the right material and a good metallurgist, important information about crack growth can be found, such as how fast the crack was growing and where it started. When handling such a part, never fit them together or otherwise contact the crack face. It will compromise the information which is there and irritate your metallurgist. Impact is another dynamic load. Now and then, those standing around a failed part will ask, "Did someone drop this?" Getting someone to fess up is often a problem. The Titanic disaster was a tragic example of loads being applied which the structure could not withstand. Even though a primary cause was known, running into an iceberg, the failure received a lot of study. Every airplane crash and many roadway crashes get studied to determine what can be done to minimize the effect and reduce the chances of it happening again. It is common for failures to be caused by a combination of events. For the Titanic, the iceberg was not seen soon enough. It is common for failures to be caused by a combination of events. For the Titanic, the iceberg was not seen soon enough. The breach on the side opened more chambers than was thought to be possible. The bulkheads between chambers did not extend to the deck above, and so forth. Look for combinations of events.